So the resource allocation games model dividing a single resource between players such that the players value the same resource or the same amount of resource, because here this is going to be something which can be divided in a continuous manner. The players value it in different manners, so the players have heterogeneous value functions. And that's also taken from this game algorithm game theory. And the resource allocation game, for example, it can model bandwidth division, division of electric current, electric power, or something. Whenever you have some capacities which need to be used and which do have a finite value, they can be modeled by this resource allocation game. So we have n players, at least 2 players, and this capacity, which is the resource which we divide between players. And so now the player's value is a function which is continuous. It's a real function from real to real, which is continuously differentiable. That's what I mean by excuse me, yeah, which is what I mean by C1 of R. We also assume it's concave and strictly increasing. We are not going to delve now into the technical conditions, but they're important for analysis. And the value function models how much the player values a certain amount of the resource. So in general, they can be different. That's exactly what I mean by heterogeneous values. And the outcome, the division of this resource, is a non-negative vector x1 till xn, such that the vector elements they represent how much capacity every player receives. So the sum of those xi's is equal to s. Now, it's not exactly a game, because we will not define what are the actions of the players and what exactly is the utility, because it's not exactly what the player values, but the player also is going to have to pay something. So now we need to define, that's not exactly a game, but first we define the social welfare, which we are going to take a look at, and then we are going to finish the finalize the definition of the game. So the social welfare is utilitarian, which is the sum of the values. And here, note that the sum of the values, if you don't sum the utilities, which will be value minus the price that the player has to pay. We just look at the optimum utilization of the value by the players. That's the social welfare. That's often the case, because people just want to optimally divide the bandwidth between those who need it, and not just to optimize the value minus the money. And the proportional sharing mechanism is one of the possible definitions to complete the definition of the game. And that mechanism receives the bits from the players, and these are the strategies. So if the strategy of the player is a bit, is a real number, a real non-negative number. And the mechanism eventually allocates each player a value which is proportional to those xi's to her bi. So it's bi over the sum of bi's. It has to be bi here. A typo, 1 second, I'll fix it. So it's her BI relative to the sum of the bits, the proportion of that player's bit, and that proportion determines which proportion of the total capacity the player gets. So, for example, if the player beats 1/3 of the bits of all the players of the total bit, then the player gets 1/3 of the total capacity. Now the value of that player is Vi of that value, so it depends on the function Vi, and the utility is Vi minus Bi. So the player pays the bit. So you say that you want that, you get the value which is proportional to what you say, and you pay. The more you claim, the more you have to pay. Now, this is defined for any non-negative vectors besides when all the bi's are 1, are 0, and if all of them are 0, we define the utilities of all the players to be 0. So that's the definition of the game. Now we have the players, the strategies are the bits, and the utilities are defined as the value of this allocation, proportional allocation, minus the bit. That's the game. And the conditions of the I, that I remind that the I is continuous, differentiable, concave, and strictly increasing, they imply, we can show it, but we don't show it now in the lecture, that UI is also continuously differentiable. One, that's trivial because UI is simply an superposition and then minus some BA. So, and strictly concave in BI. So as a function of one variable for any setting of other BIs, such that their sum is at least is positive. So pretty much whenever we are in the realm of this formula, we don't need to use the definition for all zeros. Our assumption can be shown to imply that UI is continuously differentiable and strictly concave with BI for any setting of the other betas. Now it can be proven that every any Nash equilibrium has the same social welfare, but the efficiency is not guaranteed. Now we just show an example where not every equilibrium is efficient. Moreover, we show an example where no equilibrium is efficient. So even the price of stability here is strictly larger than 1. And the example is as follows. So assume that the total capacity to be divided is 1. The value function of the first player is 2x. And the value function of any player after the first one, so the second, the third, and so on till the end, is simply the identity function. So what the player gets that is her value. Now, since the first player has the largest value, the optimum allocation, the unique optimum allocation, in the sense of the optimum allocation which maximizes the social welfare, will be allocate everything to the first player, because then that will be multiplied by 2 and not by 1. However, this can never be a Nash equilibrium, because in order for this to be a Nash equilibrium, for such an allocation to be realized, the first player has to beat something positive, and all the other players have to be zero. But if that is the profile, then player 1 will also would get everything if she just beats something positive for any positive number, because the others beat 0. So she can deviate to some value which is strictly smaller than x1, but is still positive. She will still get all the capacity, but she will pay less. So she will strictly increase her utility by this deviation. So this cannot be a Nash equilibrium. So this unique optimum allocation is never a Nash equilibrium, and therefore the price of stability, and definitely therefore the price of anarchy, is strictly positive. So we've seen 4 examples of this widely studied topic of looking at a game, finding the equilibrium and calculating their properties, mainly the efficiency of equilibrium. But this can be also used as a guide for mechanism design. So this topic of mechanism design is a very large domain which is now being studied, of course, on a deeper and higher level than what we have done. But it's very interesting because if you can bound the price of anarchy, that means that assuming the players are going to play according to some solution concept, you can say that they're going to play at least as such close to the equilibrium as the bound is. And if you can only give a price of stability, then it shows that there is at least one solution concept that the players, if they play that, so if you can convince them to play that, get close to the Nash equilibrium, as close as the bound predicts. So that's a very strong, especially when you have a bound of price of anarchy, that's a very strong prediction, and therefore it's very important to do it for practical reasons. And of course, the problems are also theoretically important sometimes. So we are now just scratching the surface of that to give you the taste of this domain. And I'm just talking about what we've been doing till now. But there is a dual domain which we are going to also very briefly, even more briefly than what we have been doing till now, describe here, so that you will kind of have a nice appetite, to whet your appetite to do something more in this area, which is also very practical and active. And that's the domain of mechanism design. So till now we looked at the game and we analyze what are the equilibria, so what are the players going to do under some assumption, and what are the efficiencies of those equilibria. Now, if we look at the existing interactions, the natural interactions we can establish, have a very inefficient equilibria, or somehow bad solutions in some way. For example, that the equilibria is to tell something which is really wrong when you have to bid in an auction or something like that, something we don't like. Then we can, of course, try to dictate something, a solution, but sometimes it's unrealistic, especially when you have a network and we don't know actually what the players think. Or we don't want to dictate because we want the players to be and to feel free. Then we actually can think of the following problem, and that's called mechanism design. That is finding a game, designing a game that possesses the equilibrium we want. So not giving a game finding an equilibrium as we do, but giving what we want the players to do, finding a game such that something will be an equilibrium in that game. And the problems here in the mechanism design can be, for example, given a class of mechanism, which mechanism can guarantee the best price of anarchy. Or given a game and a class of options to influence the equilibrium. Like you can, for example, give players subsidies if they play in certain ways, but you may not find them or something. So given a class of options to influence the equilibrium, which options will minimize the price of anarchy? And let us give the example of proportional sharing mechanism. So, and remind you that we saw that in a game with proportional sharing, resource allocation game with proportional sharing mechanism, there is no optimum Nash equilibrium. We only look at pure Nash equilibria. There is an infinite game, by the way, but anyway, we look only at pure Nash equilibria, and we prove that there is no optimum Nash equilibria. So the price of stability and definitely the price of anarchy are strictly larger than 1. It's possible to prove that the price of anarchy is actually at least 3/4. So the question is, first problem, which we can think of mechanism design, let us modify the game, so find another mechanism, so that the price of anarchy will be smaller, so that the worst possible Nash equilibrium in the sense of the social welfare will be not as bad as we have here. And now it depends, of course, on which class of mechanisms we may use. If any mechanism is allowed, then the famous VCG mechanism, pretty much the generalization of second price auction, so then that's pretty much, then everyone bids what her value is. The player who has bid the largest bid receives the object, everything, and pays the second largest bid. It can be generalized and so on and so forth. Formally, you say that the player pays the cost it incurs on the others, the total decrease in the value of the others. But anyway, there is this famous class of VCG mechanisms, Clark Groves, that's why it's called VCG, which achieves price of anarchy of 1, so optimum allocation in any Nash equilibrium. It's actually going to be also in weakly dominated strategies. And now, however, this VCG, which is a nice solution, it has the following downside. So even if we may use this mechanism, it has to be able to have very high communication complexity, both from the players to the mechanism. So each player needs to communicate the full function of the full valuation function to the mechanism, and not only one number, which is the bid, but rather what the player will give for how the player values, any real any real number which is smaller than the total capacity. So the player needs somehow to communicate all these functions. And when the mechanism decides what to do, in the proportional setting, the mechanism can simply communicate to the player one parameter, such as the sum of the bits, and the player knows that she obtains her bid over the sum of the bits times the capacity. Okay, the capacity can be, if that's not known, it can be also included in it can be the sum of the capacity divided by the sum of the bits. Then the player obtains this number times the bid, times her bid, and pays per bit. That's how the mechanism communicates to each player her decision. So one number to each player. Here in BCG, the price are in general different for each player, so that's not possible to communicate one number, the same number to all the players. So the problem now can be formulated: is there a mechanism such that the communication complexity is the same as of proportional sharing mechanism, but the price of anarchy is smaller than that of the proportional sharing mechanism? And here the answer is no. So the proportional sharing mechanism is optimum among mechanisms which have those communication complexity constraints. Okay, so that was just let's say short explanation of the realm of mechanism design. So I hope it whets your appetite for more. It's definitely a very theoretical and practically important area. And now let us recapitulate what we've done till now. So we've studied efficiency of solution concept. We've mentioned that it depends what solution concept we use, like Nash equilibria, dominant strategies, and so on. If you have several solution concepts, for example, several Nash equilibria, which we are going to actually take. So we look sometimes at the worst, sometimes at the best, and that gave rise to price of anarchy and price of stability. And also efficiency depends on the social welfare. So the way we define social welfare, usually we look at the so-called utilitarian social welfare, the total, the sum of the utilities, of the cost, but it can also be that we look at the maximum social welfare. And for given those assumptions that they decide of a solution concept and over the social welfare, we define, basically we reminded the definition we already had seen of price of anarchy and stability, which refer to the worst and the best solution concepts from the point of view of the social welfare. Now when we look at concrete examples, so at classical games where much is known, and we only look at some little parts of those games, a simple example, so a non-atomic network routing, which is not formally a game in the sense of what we have looked at before, but we could define a parallel to Nash equilibrium and so on. And there we saw this famous Pigo example, which exhibits price of anarchy of 4/3, which can be, but we don't prove it, proven to be the worst price of anarchy, which can be for a fine cost for any network, not only in Pigo, but that small network achieves the worst which can be for a fine cost, while if the cost function can be anything, then this actually price of anarchy can be unbounded. And I think you will have it on your homework. So then we look at Shapley network design game, which is a game in the realm of what's the name? Network. One second. That's one of the network formation games. Which is a very rich topic studied till now, but that is a concrete game that you have agents who each wants to connect the source with a sink, and the costs are divided between the agents who use a certain edge. And here, unlike in the previous game, in the non-atomic network routing, where the previous example had price of anarchy of 4/3, but the best equilibrium actually no. Yes. So I want to say that in this game, I'll formulate it differently. So in Shapley network design game, we find a game which has price of stability of 1. So there is an optimum mesh equilibrium. Unlike in non-atomic network routing, where the price of stability is equal to the price of anarchy, we have not proven that that's true. So when the price of anarchy is 4/3, the price of stability is also 4/3. Here we saw a case where the price of stability is optimum, but the price of anarchy is not. But then we looked at a nice example where the price of stability is also not optimal. Actually, when the price of stability is equal to the price of anarchy, and they are both harmonic functions in some parameter of the graphs. And harmonic function, I remind you that 1/1 plus 1/2 and so on, still 1/k for some k. So that was the price of stability and the price of anarchy, because it was the only equilibrium, the only Nash equilibrium at this network design game. And then we looked at scheduling games. Then for the case of looking at the social cost, which is max-span, so that which is the maximum cost, so that the worth of job is not as bad as possible, then the price of anarchy is optimum, is 1, so every Nash equilibrium has the optimum max-span. But if you look at mixed Nash equilibria, or if you look instead of max-span at the utilitarian social welfare, then we have another case. So for the social welfare that we have here, which is the max-span, the price of anarchy is 1. So any Nash equilibrium is optimal. When we look at the mixed Nash equilibrium, so they include they strictly include the pure Nash equilibrium, then the price of anarchy can decrease, and it does decrease. It becomes log over log log. So it very slowly but grows till infinity, asymptotically grows to infinity. Now, another case we looked at was the utilitarian social welfare. And there, also, the price of anarchy is 1 for pure equilibrium. But when we go to mixed, this becomes worse. But it does not become infinitely worse. It becomes 2 minus 1 over m. So at most twice worse than the price of anarchy of a pure Nash equilibrium for the utilitarian social welfare. And the other topic is resource allocation game. So the model of allocation of bandwidth or anything else, kind of pie division between players with proportional sharing mechanism. We show that the mechanism is always inefficient, and that also motivates us to talk about the general idea of mechanism design, which can be guided by equilibrium inefficiency. So if we see a game which is always inefficient, we can say, okay, can we change this, or adjust, or invent a completely new game from some class of games that will be actually efficient. So the equilibrium efficiency measures guide mechanism design. And we looked at what happens with respect to this proportional sharing mechanism. That, as I said, we can have an optimum mechanism, which is kind of VCG type, but then the communication complexity to and from the mechanism will be worse than in the case of proportional sharing mechanism. And if you may not increase the communication complexity, if they may not exceed the communication complexity of the proportional sharing mechanism, then the proportional sharing mechanism is actually optimal. We have not proved it, but it can be proved. Okay, so that was a very brief introduction to concrete games, in the sense of that we model some important situation, analyze stable states and their efficiency.